It just means there's going to be no facility until. Yeah, I'm starting to. So yeah, you don't need a mic, but you should stand. Yeah, that's the problem with it's a perfectly engineering, it's not designed to be manually so I read very few less.
Good afternoon, everyone. I hope everyone had a good lunch. Can you hear me? All right, so we're going to get started with the next session. My name is, thank you, Ori. My name is Tea Tamim, and I'm going to chair this next session, and I'm very excited to hear about the topics in this session. The topics are supernova remnants and dusty supernovae. And our first speaker is Melissa Shabande, and Melissa will tell us about supernovae as key dust producers.
Thank you. Hi, everybody. You hear me well? Good? Okay, cool. My name is Melissa Shabande. I'm an STScI fellow here at the Institute, and today I'm going to tell you about the role of supernovae in the dust formation in the early universe. Before I do that, first I want to thank the organizers for inviting me, and also I want to thank you all for being here. I'm going to start with telling you why we care about dust. Well, dust is the building block of the universe. It's behind star formation, planet formation, and if we can understand how dust behaves and scatters light, then we can understand the color of background objects better. And so some years ago, everybody believed that AGB stars were the main producers of dust in the early universe. However, JWST came along, and then we found these very high redshift galaxies that are pretty dusty at about 300 million years post-Big Bang. And AGB stars, being the main dust producers of these massive dust reservoirs in these high redshift galaxies, could not explain why we can have this much dust, because AGB stars shed their outer layers over many, many years that could not have produced this amount of dust in the high redshift galaxies. So what is the alternative scenario? Supernovae. Because supernovae are the explosion of massive stars, and then they can spread material throughout the space pretty quickly. So they can explain why we see these massive dust reservoirs in the early galaxies in the universe. So what I'm showing you here on the right is this plot from Carniani et al. 2024 that they show that even though supernovae can also destroy dust, which is one of the arguments that was used in the past, that supernovae cannot be the main dust producers, even though they can destroy a lot of dust, but these two high redshift galaxies at about Z14, that were found recently show that even with reverse shock destruction of dust in supernovae, they still are the best sort of candidates to explain these massive dust reservoirs in high redshift early galaxies. So now, Forecast supernovae are the massive and young stars that explode. Therefore, we're gonna explore these supernovae to understand and confirm if they are these main dust producers. So before I do that, I just want to show you this diagram that sort of explains dust formation life cycle in a supernova. So we start from the left. We have a supernova explosion. These dates that I have here are not exact. Depending on the type of supernova, these could change. But if we look at this diagram, we have the supernova explosion. Depending on the type of supernova, after about 2 weeks or more, we reach the maximum light, and then about 50 to 70, sometimes even up to 100 days post-explosion, we can expect to see dust precursor features showing up in the data. And by dust precursors, I mean molecules such as carbon monoxide and silicon oxide. And why do we care about these molecules? It's because these molecules can cool the ejecta of supernovae to temperatures at which dust can form. Because as we all know, supernovae have really hot ejecta, and if we don't have anything to cool down these ejecta, we cannot have any dust formation. So we can actually observe these molecules in supernovae, then that can indicate that possibly in the future we will have dust formation because the ejecta is now cooler, thanks to molecules such as CO and SiO, which have really good vibrational capacity that they can turn down the temperature. So about 100 days, depending on the type of supernova, about 100 days, we expect to see other molecules showing up, for example, SiO. And then post 200 days, we still keep seeing how these molecules evolve. And then after about 300 days, we can expect to see dust features showing up if the supernova is gonna produce any dust. And then I've also wrote some stuff here that what are the sort of characteristics of these different stages that were after. Early on, we measured the molecules, we measured or get at least an upper limit for these molecules. And then over time, we can measure how much dust is forming in these supernovae. So before JWST, we did not really have much information about how dust forms in supernovae. What we had, for example, one of the best data sets we have is about 1987A, which was a nearby type 2 supernova. And because it was so close, we could get a lot of observations, ground-based and with Spitzer. But that was pretty much just about it. And then we also could get, in the past, what we did is that we got other observations, for example, near-infrared spectra of some of these supernovae or Spitzer photometry to understand how dust evolves. But what we couldn't tell is if the dust is newly formed or it was pre-existing, or if we see a growth in dust, we could not actually tell if this growth was because of the optical depth effect or it was actually newly formed dust. And by optical depth effect, I mean that when you have a supernova that is optically thick, when you look at it at, like, let's say, early time, what you can measure from the dust mass that you can measure may not actually represent however much dust you have there. But over time, it expands and the ejecta becomes optically thin. That's when we can actually measure more dust. But that doesn't mean that supernova has been producing dust. That means we could not see it early on. But we could not tell. A lot of these stuff we couldn't figure out because we didn't have the sensitivity and the wavelength coverage that JWST provides. So now we have this amazing telescope. What we did is that we're trying to understand what's happening with dust evolution in supernovae. So this plot that I have on the right, what I'm trying to show you here is what we've had in the past before JWST. So all these dots here are showing you the dust mass measured in supernovae, mostly type 2 supernovae. over time up to 10,000 days. And we only have one data point up here that is 87A. So what we're trying to do is to fill out these gaps. So we have a gap here from 0 to 100 days. Maybe we don't have any dust, but we haven't had any studies that focuses on this time range. And then we also, if we focus on beyond 2,000 days, we also see another gap here that we haven't really had good data to measure how dust evolves. And if we can't actually understand this, we can understand how dust evolves in supernovae. So first, I want to focus on the early time, since I want to tell you a little bit about some programs that are focusing on supernovae when they're young to understand this dust formation, and later on I'm going to focus on dust formation in older supernovae. So starting with the early ones, we had a program, cycle 1, that focused on a type 2p nearby supernova called 22ACKO that you can see here. And what we did is that we observed the supernova at 4 different epochs, starting from around 30 to 50 days post-explosion. And then why we did that is to actually measure and get an upper limit for whatever dust that is already there. So later on, if there's dust forming, we can actually compare and understand if it's pre-existing or newly formed. So this was a program. We have another program, cycle 2, that focuses on another nearby type 2p supernova. The reason we have all these different supernovae that you're gonna hear more a little bit about is that each of these actually behave differently, and I will show you as we go along that they do not actually show the same dust characteristics and properties. We had another program that focused on a type 1c supernova. These supernovae are the ones that have lost their outer layers, hydrogen and helium, which is different than the one that we saw previously. They still have their outer layers intact. And in this supernova, we observed it at the same exact time as the other one. But the difference is that in the previous one, we did not see any molecule signatures in the data, because it is still optically thick or whatever other reason. But looking at a different type of supernova, we actually saw the signatures of these molecules in the data set. We saw CO and SIO pretty early, about 30 days post-explosion, which can tell us that this supernova, for example, could be one of the really newly forming dust-forming supernovae in the future. So what we're trying to do is that to follow some of these supernovae all the way, hopefully for so many years to come, so we can eventually sort of fill out those gaps that I showed you earlier. This is another program that we have that looked at a different type of supernova, type 1b. This one has helium still intact and no hydrogen, and we saw molecules, pretty strong CO molecules showing up, and possibly SIO. And then we also saw some other molecules such as PAH lines, which is work still in progress, but it was amazing to see these as we predicted in these supernovae. And by the way, these are the only IR data of these really massive explosions, strip envelope supernovae so far. So now I told you a little bit about these programs that focus on the early time, the younger supernovae. Now let's look at late times when supernovae are years, more than 300 days old. We had a program, cycle 1, Ori Fox was the PI. So what we did is that we selected 5 supernovae, type 2p supernovae that were, we called it a golden sample of supernovae because these 5 had either already had some Spitzer data or they had some sort of ground-based observations that indicated they may be hosting a lot of dust. So we picked these 5 and we studied them with JWST, comparing with all the other information that we already had. And what I'm showing you here is, this is sort of similar to the plot that I showed you where we have the gap. And the reason we picked these 5 is First, because we had some data, but also because where they fall in this plot can actually help us to constrain this regression better. So I'm not going to tell you about all of these, but I'm just going to show you two of them, 2004 ET and 2017 EAW, which were our first observations from this program. So what I'm showing you here is the image we have with MIRI, all filters included, of 2004 ET and 2017 EAW. And you can just see by looking, only by looking at the image, you can see how much brighter 04 ET is compared to 17 AW. And just very simply, if we just look at it, we can tell that maybe because this 04 ET is older, so it's been producing more dust over the years, and that's why we can see it showing up brighter in all these IR filters compared to 17 AW. And what we did is that we modeled the SED of these supernovae, and we actually found that both of these look pretty different. For example, 17 EAW has two distinct silicate emissions, while 04 ET shows an optically thick dust composition. Just want to mention, even though they were the same type, they did not show the same. They behaved totally differently. So we had another program, cycle 1 again. Ori was the PI, and what we did for this program is that we tried to focus on a different type of supernovae called interacting supernovae. And the reason we did that is that I'm using this plot to show you sort of why we cared about these supernovae. If you look at this plot that shows the brightness of supernovae versus time, you can see that interacting supernovae fall over here, meaning like even up to 1,000, 10,000 days post-explosion, they are still pretty bright in the IR, and all these data is from Spitzer. So when we saw this, we decided that we're gonna observe another 5 supernovae, interacting supernovae, to see why they are brighter even so many years after explosion. So what we did, I'm not gonna show you again all of them. I just picked one of them that we think it has the best data. So 2005 IP is this supernova that was pretty bright in the IR in Spitzer data, and we had Spitzer photometry plus Spitzer spectrum, and this is the only one that we had a Spitzer spectrum of among all this sample. And then we got a JWST spectrum about 20 years later, and you can sort of see here how they actually look very different. So what we think is happening is that maybe early on we had some hot carbon dust. That's why we don't really see silicate emissions. Or maybe at the time, about 3 years post-explosion, this supernova was still very optically thick, so we couldn't actually see through the ejecta, so we couldn't actually see if it's silicate emission there or not. But looking at the JWST spectrum, you can see there are 2 distinct silicate emissions. And when we measure the dust mass compared it to the Spitzer data, we realized that this is even hosting more dust, meaning that it could actually keep producing dust over the years. And we concluded that this is mostly seems like it's a newly formed dust in the supernova, which confirms the idea of supernovae being one of the main dust producers of the early universe. And yeah, so this one was 3 years after explosion, this one about 18 to 20 years after explosion. And the dust mass that we measured in the supernova was the highest dust mass ever measured, aside from 1987A, which was this nearby that I showed you earlier. So why interacting supernovae could host a lot of dust, the one that I just showed you, one big idea is that they have something called this cold dense shell. So if you look at here, these supernovae that have lost a lot of their outer layers over time, when they explode, the ejecta interacts with the CSM, and it creates something called the cold dense shell, that this cold dense shell is protected from the reverse shock and the forward shock of a supernova, which are the ones that actually destroy dust. So we can have this shell that whatever happens in there, and if there's anything forming there, if it's protected from all these shocks, then it can actually, over time, host more dust, and the dust that is newly formed can be protected. So one big idea that is out there is that this cold dense shell is what that contributes to these interacting supernovae having a huge dust reservoirs. So I'm going to just quickly mention some other programs that we've had. We actually observed not only the strip envelope supernovae, interacting supernovae, but we also found another supernovae in our data set that is a type 2L. I'm not going to get into the details of how they are different, but again, we did not find a similar sort of composition as the other ones. And it showed that even out of like 4 or 5 supernovae that we looked at early on, they all behave differently. So I was told that we need to answer some questions as invited speakers, so I chose 2 of them. So one was that what were some of the most exciting opportunities enabled by space telescopes, both hardware and policies? All the stuff that I showed you shows how much JWST has helped us already just by looking at this very small sample over 2 to 3 years that has already helped us to fill this gap. You can see like 2 of them, of the data points that I've plotted here are already filling this area. And then we have some other data coming up that fills out the younger time range in dust production for supernovae. And then, so since I was telling you about this diagram, that supernovae, when they're young, we try to study them, to look at these molecules, blah, 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 to get to dust production many years later. So what I showed you so far is these supernovae that are about maybe 20 years old, but then we can look at, as we go, this life cycle continues. So like, for example, 1987A, which was a nearby type 2 supernova, has been studied pretty well, has a lot of JWST, Spitzer, and other ground-based data. I'm not going to get into this one, and I think the talk after me, Josephine is going to tell you a little bit more about this one. And then if we go even further, like older and older, then we get to supernova remnants, which again, when we get these amazing data, you can actually focus on different parts of this amazing object and understand how dust has evolved and the composition of dust in supernova remnants. So another question was that what were some of the biggest challenges you faced when using space telescopes? I think a lot of you are familiar with these. So I would say one of them was data reduction, because a lot of our pipelines initially were not focused on, more focused on like galaxy studies. And we had to make a lot of sort of optimize the pipeline so we can actually process our own data. And then I think another maybe challenge is budget cuts, because maybe there's not enough, there's not enough budget to actually provide the manpower that we need. Sorry, I'm done. Manpower that we need to process all this stuff that is coming up. And then going back to this cycle, as you can see, we have a star explodes, and then as it gets older, we're studying it, and then we have something like 87A, 30 years later, we can still study dust, and then we have remnants, and then remnants, all this stuff that is spread throughout the universe creates stellar near series, and then this cycle continues. Thank you so much for listening.
Questions for Melissa?
So your results confirmed what we saw, I think, in 87A of the very few dust at the beginning, and then you wait 10 years and there appear to be much more dust. Do you have any constraint on whether it really was formed more dust, was hidden and it got shown, or even it was pre-existing dust that got swept up?
Yeah, that's a great question. That's one of our main goals. Going back to this plot, this one. So these measurements that were done in the past, we're trying to do a more careful job of understanding the composition of the dust that we're measuring with JWST and measuring the dust mass. But what I'm showing you here is sort of a mixture of whatever dust mass we measured at the time, meaning like some of these could be not newly formed, and just like as we observed them again over time, they got optically thin and we measured more dust, but didn't mean necessarily that there was more dust forming over time. Or some of them could actually be that. We don't have enough information from these because some of them are just photometry from Spitzer. But right now we're trying to do a careful job of understanding if it's a pre-existing or newly formed, and then redo this plot later. So we still don't have enough data to say that.
So thank you so much. So I was wondering for O5IP, I think you showed that in early times it had silicate base and then later it has carbon. This was the other way around.
It was the other way around. So the yeah, this one.
So I'm curious because sometimes I mean a lot of people in the field have worked on looking at the composition, as we said, and then saying, well, this makes sense for the progenitor structure, and then also if you talk to people in the dust community, right? When they talk about the composition, it seems like they have very different panels in many ways. So I was curious if you had any thoughts about the fact that you see both kinds of the same supernova at different times. Is it something that has to do with the progenitor, or is it just something kind of more messy astrophysics?
I'm not sure if it's about the progenitor, but what I mentioned here is that it could be carbon dust. But what we actually think is happening is that this was also majority silicate dust in the cold dense shell, same as what we see here. But since at 3 years, about 946 days, this one was still optically thick, we could not actually see the silicate emissions. So whatever we measured here is total dust mass, which is still the same when we measured it again, but we could not see the emissions because possibly it was optically thick at the time. And then right now, we can actually see silicate in the data better. Thank you.
We have to move on to the next talk. Thank you so much. Our next talk is by Josephine Larsen, talking about space observations of supernova remnants and the unique case of supernova 1987A.
Okay, so how do I? Okay, thank you. So I'm very happy that remnants are included in this meeting about transients, because although they evolve on much longer timescales than the young transients, they of course provide really crucial information about the explosions that's highly complementary to what we learn from the more distant objects. So I'm going to talk mainly about supernova 1987A and focus primarily on what we learned from recent JWST observations. But let me start with some just background on remnants. So supernova remnants are really important because they give us a spatially resolved view of all the many complicated things that happen when a star explodes. We can directly observe this asymmetric explosion geometry. Sorry, I was trying to use that. Okay. In many cases, we can identify the compact objects and study their properties, and we can study all the details of the CSM interaction with spatial resolution and learn about the progenitors. Also, supernova remnants emit multi-wavelength emission, so of course we need space telescope to characterize all this emission, as illustrated by this nice color composite of the crab. So I just wanted to highlight a few things. So first, if we go to the X-ray range, you see these wonderful images from Chandra of all the shocked ejecta and CSM, as well as the pulsar and the crab. XP has kind of added a new dimension to this by measuring X-ray polarization, so we can map out the magnetic field structure. As we go to harder X-rays with NuSTAR, we can probe the radioactive decay lines from titanium-44, which has another really important diagnostic of the explosion. So you see the lines here in 87A, and it's actually resolved here in the case of CAS A, you see the asymmetries. I want to move on to the infrared range, and I want to show you these wonderful images of supernova remnants observed by JWST, some of which were already shown in the previous talk, but I think they're worth looking at again. So they're ordered by age, from the Crab to CAS A and supernova 1987A. And this infrared emission provides a lot of useful information about the ejecta interaction and the compact objects. And I'll talk about some of these topics in the case of 87A. So let me take you back to 1987, when this thing exploded in the LMC. And because it was so nearby, it of course enabled a lot of unique observations. Famously, we had neutrinos. It was the first time that the progenitor could be identified in pre-explosion images. So here it is, 20 solar mass star, blue supergiant. And this supernova was also really well timed with the launch of HST. So here's an image from early in the mission. It's the supernova in the middle, and you see this system of 3 rings of circumstellar matter that was flash ionized by the supernova. So they're inclined towards the observer, which is why they appear elliptical. And here's a much more recent image, and you see a lot of things have happened. The ejecta have expanded to reveal this highly asymmetric morphology. And the fastest ejecta are interacting with the ring and material around it and giving rise to this complex system of shocks. So HST has been really important in following this time evolution. And I've just updated this to show you 3 decades of HST observations and the intense efforts by so many scientists to keep writing these proposals every year. And as you see, we go from here to here, ejecta have expanded and changed, it's faded also. And from the kind of early 90s, you see these hotspots appearing, which is the fastest ejecta impacting on the ring. And we get this emission from shocks. That first brightened till around 2010, and then it's been fading. The blast wave has gone through, and we see more emission outside. And from this wonderful data set, we've learned a lot about the time evolution. We can study the energy sources pairing the ejecta and the propagation of these shocks. Of course, HST is not the only telescope that has been following 87A. I just wanted to show you another example from Chandra. So this is from recent work by Arvind Ravi, where in this case, we don't see the ejecta directly, but we can trace the shocks in the ring, follow the light curve and the expansion. So we see soft X-rays behaving in a similar way as optical, and also harder X-rays from faster shocks. If we move on to another wavelength range, I want to move on to the infrared again, and of course JWST, which has really opened a completely new window on this supernova. This object was observed early in the mission. There was a GTO program with MIRI MRS plus imager, as well as NearSpec IFU, and then also a program with NearCam. And one of the most exciting results to come out of this, I think, is the discovery of narrow emission lines from argon right at the center of the system, which is telling us that the compact object is ionizing the innermost ejecta. And I'll tell you more about those results later. We observed 87 again in cycle 2, both with the MRS as part of the GTO program, as well as with the NearSpec IFU, and now importantly with better spectral resolution. So comparing the data in the 2 cycles, we can study time evolution. There's a paper in preparation by Patrick Kavanagh with all the MRS results, and this is just 2 examples of difference images. You can see how the emission from dust in the ring evolves. It's mainly fading, but brightening in the outer parts. And we have also this strongly increasing emission from interaction of the inner ejecta with the ring. From these observations, we also learn more about the compact objects ionizing the innermost ejecta, as well as the 3D distribution of material. So I want to start with the last point, the 3D distribution. And the reason we're interested in this is, of course, that these asymmetries and the mixing of ejecta tell us about the explosion mechanism and the structure of the progenitor star. And in 87A, we're really fortunate in that the ejecta inside the ring are just expanding freely. So distance from the center is just the velocity times the time since explosion. And so images gives us 2D, and the Doppler shifts give us the third dimension. So when we have an IFU, like with NIRSpec, we have the spectral information in every pixel, and we can get 3D information. So this is an example for molecular hydrogen. So you see the highest blue shifts, some kind of low blue shifts and red shifts, and the highest red shifts. And we can do a full volume rendering of this. So remember the inclination of the ring, and the observer is located here in this plot. So a couple of things to keep in mind when looking at this. This looks a little bit stripy because we have better spectral resolution than spatial resolution. So we're solving smaller velocity structures along the line of sight. And then, of course, this probes the distribution of ejecta, but also energy sources and dust, possibly. We can do these kinds of 3D maps for a lot of lines, and I'm just showing you a selection here. So this is first as projected on the sky. So we were just looking at the molecules. We have iron 1, so this is actually from cycle 1, silicon, helium. You see some more emission in the interaction regions. Two different views of this blend of silicon 1 and iron 2. Because if you include the full velocity range, it's just completely dominated by this interaction region. Whereas if you restrict it, it looks like this. And comparing the different iron and silicon lines, we find that it's really silicon that dominates here, whereas this is iron 2. We can look at this asymmetric distribution from just another viewing angle. So this is with the ring plane, and you see a lot of the emission is concentrated to the plane of the ring. And especially for the iron and silicon, it's dominated by kind of two main clumps, the southern one being a bit further below the plane. And this, I should note, this looks smoother because of the lower spectral resolution in cycle 1 with this line. I also wanted to point out, you see these interaction regions I was just showing you, they're really right in the plane of the ring. So here we're most likely interacting with the reverse shock. And I just put these together so you can compare. So to the left, you see the iron 1 and silicon 1 really have very similar distribution, whereas this is the iron 2 in the interaction region. And then to the molecular hydrogen and helium, you can hopefully see that the molecules have a bit more compact distribution. So from all these wonderful observations, we can, of course, kind of quantify and compare all the different elements. And I'm not going to go into all the details, but just highlight a few things. So if we identify the brightest peaks in 3D, it forms kind of a misaligned dipole, as illustrated here in 3 kind of viewing angles. Whereas the 3D velocities of both peaks are just above 2,000 kilometers per second. We also, in addition to this, there's lots of substructure with clumps and rings. I wanted to show you the NIRCam image that gives us better spatial resolution of this 1.64 micron blend, though it doesn't capture the full velocity range because it's a narrow filter. So you have 2 rings and something going across, and you can actually kind of make out the similar things in NIRSpec, and especially if you restrict the redshift range, you see the similar things. And one more thing is that we can also look at the distribution of the outer hydrogen and helium-rich ejecta from the reverse shock, which I didn't have time to go show you the details. But this is, we still have this kind of global asymmetry, so stronger here and here, but overall it's more symmetric. So right now we have, I think, a lot of interesting work ahead of us to compare with simulations and see how we can produce this very strong global asymmetry that we have in the explosion. So I want to next change topics a bit and move on to this compact object. So the lines I was showing you just now, they're very broad, extending out to 4,000 or 5,000 kilometers per second. So this, which is the very narrow lines that we discovered in the IFU data, is something very different. So we're seeing here argon 2 at 7 micron in the MRS and argon 6 at 4.5 in NIRSpec. And we also have sulfur 3 and sulfur 4 with similar properties. So this very small highly ionized emission region right at the center can only be explained by ionization of the innermost ejecta by a compact object. And that's shown here with models, photoionization models from Klaus Franzson. So in the top panels, it's the ionizing spectrum is dominated by the non-thermal spectrum from a pulsar wind nebula, whereas here it's the thermal spectrum from a cooling neutron star. A key ingredient here, you already heard about the dust. We do need dust absorption to make sense of the line ratios, and given the various uncertainties we have with the exact properties of dust and so on, we can't really discriminate between these two scenarios. So everyone's very happy that we finally have this signal from the compact object, but there are many questions remaining, like what's the nature of this object, and all the details concerning the physical properties of the innermost ejecta. So one thing that you can note from the models is that they also predict a lot of lines at short wavelengths. And we couldn't really say anything about those for the cycle 1 because of the limited spectral resolution, and we had so many blended broad lines. So this is why the cycle 2 data are very exciting. And I want to show you first the results for Argon 6. So this is cycle 1. We improve, and that's cycle 2, and now it has 2 peaks. So what's going on? Well, we have the IFU, so we can check. You see this peak here. You see the central source. Continuum is mainly dust. If we subtract it, we have the central point source. Whereas this thing, it looks like this. You see there's a faint trace of this, but it's mainly diffuse emission that was contaminating this observation. And we actually see similar things for many other lines. So we can now get rid of this contamination, and we have nice agreement between Argon 2 and Argon 6, and we can constrain all the properties of the Argon 6 in more detail. So one interesting implication is that this blue shift of minus 250 and the slight offset from the center that I hope you can see here could translate to a kick velocity of about 500 kilometers per second, assuming that the neutron star is very close to the line emitting ejecta. So this was Argon 6. I also promised you a search for other lines. So we could find 3 lines with similar properties. So the blue shift, the same location, and the narrow line profile. So in the near spec range, we can identify a narrow peak from IN2 at 1.64, calcium 5, and you see there is something here and here. But they're quite weak, and they're heavily blended with other things. This is mainly silicon, and this is mainly molecular hydrogen. And actually, a more detailed analysis of the MRS also seems to show chlorine 2 at 14.37 micron with similar properties. So we've added iron, calcium, and chlorine to our list of lines from this inner region. But there's something very funny going on with the calcium. So where there is calcium 5, we expect calcium 4 with similar properties, but we don't see that. We see instead something that's north of the center and slightly redshifted, which would imply this situation. So we're looking from here. We have these all argon-like lines, and then there's just calcium 4 on its own, which is not expected. The calcium 4 and calcium 5 should go together, and as far as we know, there's no such thing as just a blob of calcium-emitting ejecta. So most likely, it's dust to the rescue again. So I was talking about dust absorption before, but as we go to the short wavelength, scattering becomes important. And you see examples here, the dashed lines for different grain sizes. And the important point is that this increases quite sharply as we go from calcium 5 to the calcium 4. And if we have dust scattering in expanding ejecta, this can lead to redshifted broadened profiles. So just to illustrate the point here, this is for expanding spherically symmetric thick shell. For low optical depth, we just develop this red wing. If we increase it, you get this more broadened redshifted profile. So most likely this is what's going on, and this is also explaining why we don't see a lot of the other narrow lines we were hoping to see, and it would also imply that this IN2 line, for there to be a surviving narrow component, it must be quite intrinsically strong. So in summary, for these new observations of the innermost ejecta, so in addition to all the things I already told you, we haven't found any significant time variability of these lines on these timescales, and there is nothing in the continuum that would indicate a pulsar wind nebula. And right now, there are very intense modeling efforts ongoing to use all these results to constrain the properties of the ejecta, the dust, and also the compact objects. So I'll ask you to stay tuned for those results and show you some first key takeaway messages for 87A is that we see significant changes every year. We have this highly asymmetric explosion geometry and now also this signal from the compact object. I also wanted to highlight a few things that we learned from observations of 87A to just connect to the broader discussion. One thing, as I hope I've convinced you, is that IFUs are amazing tools for studying supernova remnants. We can disentangle all these emission components that overlap in projection and get 3D information. This regular long-term monitoring of the time evolution has been really important, which, yeah, we can discuss proposal policies regarding monitoring. And also, as we've seen, there's really a very wide range of science topics in a single object. So remnants is really a very nice way to spend some of your telescope time. A few other things in terms of future prospects for space observations of supernova remnants. So just a few of the very many things that could be discussed. Of course, now we have this amazing opportunity with JWST, and we want to use it to learn as much as we can about remnants. So we can, of course, a lot of things to be discussed about science topics and observing strategies. So I was talking about how great these IFUs are, but a challenge is that all the bigger remnants, unlike 8780, of course, don't fit within these fields of view. So you have to think about what parts you want to cover. And in connection with that, I just couldn't resist showing you. This is from just a few weeks ago, another remnant in the LMC called SNR 0540, where there's a lot going on right in the middle, including these rings of ejecta. Another challenge with remnants, I guess, is that they're actually in limited supply, the nearby ones. But as observing facilities improve, we can, of course, do more with more distant remnants, as well as younger objects, which are maybe transitioning to become remnants, so to connect with this transient theme. And I also finally want to connect back to the X-rays I was saying in the beginning are very important for remnants. We're all very happy Chandra is going still, and the community should start preparing for the next generation of X-ray telescopes. But it seems like Athena and hopefully Lynx is still quite a long way away, so it's likely that there will be some gap in between, which is, I think, a challenge for the community. And I think I'm out of time, so I should stop talking. Thank you very much.
For great talks. Questions?
Is the ionization inferred from the central object consistent with the other arguments that have been put forth for evidence of the central object? One was, I believe, of UWN, and one was, I believe, another thermal emission.
So one thing is this dust blob in the ALMA. So we've been so it's a peak in the dust emission in ALMA, which one of the proposed explanations was that was due to heating by the compact object. So we've been comparing positions, and the ALMA blob is actually north quite significantly of this JWST source. If you account for all the astrometric uncertainties, they kind of just about overlap at 3 sigma. And also the ALMA observations are from 2015, so there's an expansion effect. So we can't conclusively rule out that they're connected, but it seems like they're actually spatially separated. So if they're both connected to the compact object, then it would imply that it's maybe an extended pulsar wind nebula and something comes out in dust in one end and this emission lines at the other end. The other thing is that it's also, sorry.
But do the fluxes match? That's what I'm.
Oh, the fluxes, I think there is enough freedom in this, so that's fine. Other evidence suggested evidence is the hard X-ray emission from NuSTAR. I guess the challenge with that is that NuSTAR doesn't spatially resolve the system, and we would also expect some hard X-rays from the shocks. In terms of matching fluxes and so on, I think we're still consistent, but there's still quite a lot of freedom in the models.
So these images are amazing. You can see the reverse shock where the dust is. Is there an estimate of when the reverse shock is going to cross the dust region, and we can actually test the models for survival of dust?
For dust destruction, so I think that's still quite some time away. Also, the velocity of ejecta that's just reaching the reverse shock is something like close to 4,500 kilometers per second. And most of the dust we think is within like 2,000 kilometers per second. So that's still quite a long wait, but there could be less dust further out, so then that could happen sooner.
I have a quick question. I know that some JWST monitoring observations have been approved, which is very exciting. Can you say a little bit about what we might look forward to and what we hope to see?
Right. Yes, we had the JWST results today. I guess this region here is really showing dramatic brightening because it's the inner ejecta. So like this part, that's now directly impacting on the ring. And this is leading to a dramatic increase in flux, and it will allow us to probe the ejecta density profile as this progresses.
We have to move on to the next talk. Thank you so much, Jesper. Our next speaker is Arka Sarangi, and he will give us a theoretical perspective on dust formation in massive stars.
Okay, so very excited to be here. So I will be talking about how actually dust forms and what happens before and after explosion. So if you want to literally get hold of your favorite transient, I may be able to tell you something about it. Dust forms, you have heard now in two very interesting talks that dust forms in supernova. We already know that, but it is indeed quite challenging to find conditions to form dust. And why is it so? Because in the galaxy there is hardly any sources which provides us environments for chemical reactions which leads to forming dust grains. However, interestingly, evolved stars in the late phase and explosions like supernovae produces exactly the right amount of density, temperature, ionization conditions which can lead to chemical reactions, and that leads to dust formation. So what do I mean by that? We mean that whatever elements were produced at the explosion, all these alpha elements which we know are in dust, they go through series of chemical reactions. So in supernovae, often we find oxygen-rich and carbon-rich regions to be segregated in a different layers, like its pre-explosion burning phases. And so these all goes through different channels to produce clusters like these guys. And what is special about these guys are that their ground state energy levels are so stable that they do not go back to their gas phase elements, and with time they only grow towards producing dust grains. And what does that mean? That means that when we have a cluster like that and we have elements fall, like some kind of elements falling on it, this is a carbon cluster, pure carbon, and we have hydrogen, oxygen, molecules of carbon monoxide falling off it. Some of them get attached easily, some of them gets thrown away, some of them take a part of its elements away from it, and that's how we grow. And when the temperature is high, densities are high, some of them leave it. That defines the sublimation conditions of these grains. So when we say that dust is evaporated, that is basically what we say, that the rate of infall versus rate of elements leaving this has to be balanced to actually grow these particles. So that is how dust is formed. And in the modeling work, we take into account all these processes together and see, given the conditions, what will happen in different type of environments. These different type of environments are like that. Like we have hard supernovae can be of different types. All of them comes into these varieties. If I look at a 1D picture, you have a metal-rich core of a massive star. It has some kind of hydrogen. That hydrogen could be on top of the in the envelope when the star has exploded. It may have left also. Also, it may have taken some of the helium out of it. And it can be a combination of all these. Now, that mass which has left could be sitting very close to the star itself. It might have gone far away. The densities change accordingly. All these different scenarios happen. Now, in order to produce these conditions is a bit of challenge, and we had been trying to do that using a single star model, and we have used conditions called like super winds, which is based on the L by M ratio, and we have induced the faster pulses in the code mesa, and we have tried to see that when we have fast pulses, what happens is that there is a escalated pulsation, and that leads to M decreasing more, and that creates even more pulsations in the later phases. So what I am showing here is that in a 17 solar mass progenitor, by the time of carbon burning comes up, we have already lost, in these conditions of super wind, we have already lost around 7 to 8 solar masses, and around 9 is left. And we do see pulses with mass loss rates almost going towards 10 to the minus 1 in some cases. These are very short-lived though. So these pulses go for 2 to 3 years maximum, but it reaches very high conditions of mass loss in this particular progenitor. And to mimic how it will look in the density profile when you have pulses like that, and what is the escape velocities of the winds from the surface, using that we are trying to create the condition which may lead to two. One, a CSM very close to, so when I say carbon burning, it means it is around 100 years before the star has exploded. So I'm trying to create conditions where you will have a dense CSM, and we are trying to create conditions where a majority of the mass will be lost before the star has exploded. Summarizing all that, we have seen two different, one like normal winds, which is line driven, and one is with these fast pulsations. And what we find is that when we induce fast pulsations below 16 solar masses or below 17 solar masses, nothing changes. But the stars which are more massive than 17 has a huge effect of these pulsations, and it loses a large amount of mass. So these are kind of progenitors of type 1b, 1c, 1b, and 1cn. If these affect into creating fast pulses in these massive stars, which does not affect stars smaller than 17. So that leads to a kind of a theoretical approach of how you can produce stripped envelope supernovae and how you can produce CSM close to the star. Now I will talk about dust, of course. So those mass I was talking has been lost. So those mass are now on its way out. So this picture shows that when the mass loss starts over here, say at t equal to 0, then if you have a mass loss rate of -2, you will form dust in that wind around 4 to 5 years after that. When you have -3, you will need around 10 years, 9-10 years to form dust. When you have -4, you will form around 100 years it will take to form dust in the winds. And those dust are mostly silicate because the wind is the envelope, hydrogen-rich envelope, which has a abundance of oxygen-rich elements than carbon. So you will form silicate dust in that gas, and it takes these many years. So if you look at this density structure, which mimics a IXF again, in the density structure, you will see that you will be seeing some dust between around 3 times 10 to the 15 to this end. The below that, the temperatures are too high, and also the time has not yet, the wind will not get enough time to produce in these regions. So you can actually get a column density of dust have been formed by the wind. in the second, like when the density of the CSM was lower for IXF, there is still some dust have been produced, but the densities were much lower. This is just a model of 1D how to produce dust. Now, when the supernova explodes, so these are all that has happened before. Now the star has exploded, it has created even more complicated conditions. I was into this case where we have a CSM. Okay, so if we do have a dense CSM surrounding the star, then we will have a forward shock and reverse shock, which will be initiated very early on. They are very close by also, like they almost are inseparable in distance. But in between that, the mass piles up as the gas, as the shock moves forward. And this column density of gas in between are actually a very ideal site of dust formation because of high densities produced in the radiatively cooling shocks. And in this picture, I am showing that based on the abundances, if you have hydrogen-rich gas, if you have oxygen-rich gas, if you have helium-rich gas, the cooling times will be different. And so these are the cooling times for CSM and ejecta. Ejecta is more oxygen-rich. So if it is shocked by the reverse shock, it will cool at a different pace. And what is the cooling time as a function of the time since a parcel of gas has been shocked. So assimilating all these conditions, which include shock velocity, CSM density, explosion energy, abundance, mass of CSM, together will give you the rate of dust formation in different mass loss rates. And that's what this figure tells you, that how much dust you will produce in the same gas that was lost before. In the previous slide, I showed the red supergiant winds. Now this is after the explosion, what that will, how that will evolve in the region between the forward shock and the reverse shock. Now finally, the most popular place of supernova, which is the ejecta. The metal-rich part, it can produce dust very efficiently. So here I am showing that how does dust form in the metal-rich part. So simulations say that early on dust forms mostly in silicates and in the inner parts. With time they proceed 800, 1200, 3000 days. At 3000 days, you see dust has been produced in velocities close to 2500. And this blue one is carbon-rich dust, which was not there until 1200 days, but it has appeared around this time. So these are the models of how dust is produced in the ejecta, the metal-rich part of the supernova. Now I bring all these things together, and what is the final dust production versus progenitor masses in solar metallicity results. So this is interesting, and I do need to say one or two things. So these are silicate dust and carbon dust versus progenitor mass. This is progenitor mass and this is dust produced. So you see a lot of fluctuations in the masses, and we had been focusing on that, and we had been trying to go back to what has happened during the evolution of the stars. And you see that the mass of magnesium and silicon that was present in different progenitor masses also fluctuate quite a bit. And these are actually phenomenological, not really model dependent, because of the mixing that happens between the convective layers. Sometimes the temperature becomes efficient to produce more silicon. Sometimes it becomes conducive to produce more carbon and neon. That changes so much in small ranges that there is no actual way to predict a nature which does not have these fluctuations. And that is reflected in the amount of silicate dust you will produce as a function of progenitor mass. But still, if we try to generalize, it would look something like that. The silicate dust mass will increase over the progenitor mass time, and the carbon dust will decrease in a very general way, and there will be a switch around 14 solar masses. Now, different explosion models also give different results. I am showing how much it is different between MESA and Kepler, which are two stellar evolution models. The amount of silicon, magnesium, carbon it produces, it can almost create 1 order of magnitude difference in the total mass you will produce after the star has exploded. And then you have to weight it by the IMF, by the lifetime of the star, by the survival rates. If you put them all these, then you will actually get how much dust supernova will produce in a galaxy. Now I'm almost there towards the end of my talk, but since I'm talking about progenitor mass, dust production, does it happen in lower masses as well? We did explore type 1s to see if we can produce dust, but we couldn't. but there are a subclass called type 1AX. You are familiar with this, and we tried to model if we can form dust in type 1AXs. And interestingly, we are seeing production of iron-rich dust in these subclasses, which is interesting to me because iron dust is an important dust species in the ISM. And this is showing how much iron dust you can form in type 1AX supernovae. So Melissa already talked about filling these gaps that Ori's program is doing. And I'll skip this slide because it will need some explanation. And these are the team of people. I have recently formed a team in Indian Institute of Astrophysics working on supernova. And also check out Sana's poster. It will be very interesting on how to observationally look at these objects that I have talked about. So these are my conclusions. Thank you.
We have time for one, maybe two questions.
Do you have any extrapolation how dust formation would look like in pulsational pair stability supernovae or in full-blown pair stability supernovae of different flavors?
And I don't have an extrapolation. I have some ideas, but the models are yet in a very nascent stage. You have to, we have to actually model them. But yeah, it is of interest, of course.
Thank you so much for this wonderful talk. One thing I was wondering about is for the progenitors that you mentioned. I mean, there are many different progenitor models. Especially you showed Mesa versus Kepler, right? And you also mentioned Laplace, where they showed that the binary aspect of strict envelope supernova changes actually the structure of the star. So I'm curious if you have any comments on which progenitor model you use or what are kind of the pros and cons.
Yeah, so no, not really. Like, as in, we used to use the Kepler models for a long time, but we have recently tried to explore, because of the silicon magnesium problem we encountered, we are trying to explore more models to what are the conditions. And these are all single star models. Binary will change the picture much more. These are all I talked about are single star models on how they evolve in their late phases.
Let's thank Arka again. And the last speaker of this session is Kirsty Taggart, telling us about type 1BN supernova with a detected progenitor system and silicate dust formation.
Okay, so hi, I'm Kirsty. I'm a postdoc at UCSC, and I'm hoping to convince you in this talk that 2023 FYQ is one of the most exciting supernovae of 2023. It's a 1BN with a detected progenitor, and we think silicate dust. And so as a quick introduction to 1BN supernovae, you can see one of the most well-studied 1BNs, 06JC, and this is its optical spectra. It has narrow helium lines of the order 1,000 kilometers a second and little to no hydrogen. And we think these are the explosions of highly stripped stars, where the hydrogen has been stripped long before explosion, and then the supernova runs into a helium-rich circumstellar material. And these are very exciting objects because they're very rare. They're only a few % of core collapse supernovae, and their progenitor scenarios are also very varied. So originally, people suggested Wolf-Rayet stars because their wind speeds are similar to this 1,000 kilometers a second. Or potentially LBV eruptions could produce this material, but more kind of recently binary interactions have been invoked, and it turns out you don't even need a massive star to produce these explosions if you have it in a binary. So sort of low mass helium stars appear to be able to explain these objects too. And so a quick introduction to their light curves. As Dan was talking about earlier, they're very fast evolving, so they rise pretty quickly, and they also are very luminous, and they decline pretty quickly too. And their primary powering mechanism is thought to be CSM interaction. There's a lot of variety in the light curves, and we think this is due to the CSM density and the sort of CSM structure as well. And so 2023 FYQ is the closest type 1 BN supernova. It was discovered in the Virgo cluster at only 18 megaparsecs. So that's kind of the first reason why it's a really interesting supernova to study. And so on the right here is the light curve between 1 to 4 years before explosion. And you can see that this has not been seen before in any 1BN supernova. It's sort of gradually increasing up to the time of explosion. And this allowed Sean Brennan in the ZTF collaboration to obtain optical spectra actually even before the star exploded. And so this is a plot of the narrow helium features seen, and it's a very complicated line profile, but we think that there is sort of a narrow CSM interaction line, and then potentially sort of a quicker velocity line from the ejector. But this is, yeah, a very, very complicated line profile, probably with some electron scattering involved as well. And so this is a zoom in of the light curve. And so the supernova's already had 3 papers on it. And so we can see we had this sort of long gradual rise. But about a month before explosion, you see a much more pronounced rise. And so in Yizer's Dong's paper, they attributed this to likely eruptive mass loss just before the star exploded. And so the really kind of lucky thing and very interesting thing was that JWST pointed at an AGN for David Rosario's program, and the supernova was right in the edge of the image, so it was in 1 out of 4 dithers. And so this was very fortuitous, and this is the sort of first JWST pre-explosion imaging of the supernova. And so to kind of detract from this a little bit, I'm going to just quickly go on to the progenitor, which was also observed with Hubble data. And so we managed to get an adaptive optics image and locate the progenitor star. And so this is the progenitor here. We think that there is some cluster contamination, so will need further work to follow this up in due course, and we have the Hubble program to do that. But you can see that the light curve points, the progenitor points from the UV through near infrared are very blue and very luminous. And so the only thing that could sort of we can fit for the models is either a very young cluster, which has no sort of Balmer break, or Wolf-Rayet stars, but of very high luminosity, which would put FYQ on somewhere like Eta Carina. So this will require more work, but this is kind of another interesting side note to 23 FYQ. And so back to the JWST data. This is the AGN you can see in the top, and a zoom in of sort of where we had data which covered pre and post explosion. And so you can see on the right that the supernova is marked with the crosshair, and then on the bottom that is post explosion where we triggered JWST follow-up. And you can see that the star is sort of redder in the 18 and 21 micron filters, and it's much brighter. And so we know there's been a significant evolution before and after explosion, which is very exciting. And so I'm just plotting the data here. This is 20 days before the likely time of explosion, and I'm plotting the progenitor here because it is significant, around 9,500 Kelvin at this epoch. But I'm also showing the 5-band JWST imaging. And so originally when we were trying to interpret this data, it's pretty hard to fit anything beyond sort of assuming a single composition of dust. And so this was sort of best explained by a carbonaceous dust around 220 Kelvin. But this motivated us to trigger a JWST DDT program. And so we got MRS follow-up of the supernova. And so this is the spectrum. And there has been a significant evolution over the year. There is very strong silicate features at 10 and 18 microns. And so initially when I saw the difference in flux, I sort of interpreted this as newly formed silicate dust. But as Melissa was saying, it's all about sort of the interpretation of figuring out whether it's pre-explosion or it's formed sort of in the cold dense shell. And so fitting models to this sort of silicate spectrum, you find that a pure silicate model can't explain the flux below about 8 microns. And so you need a warm, carbonaceous component. And so we think this is made of sort of, as a double component composition. And so using this information, we sort of assume that because this is sort of optically thin, we think this is formed pretty far out. So this is actually potentially an infrared echo. And so we model this and try to figure out, okay, so if we think the supernova might be hitting this dust at a large radius, could we explain the pre-explosion flux? And so it turns out we can. If we heat the silicate dust to only about 50 by 50 Kelvin, we can explain the spectrum. And so we sort of interpret this as an infrared echo, which is, so I'm plotting the derived lower limit on the radius here for the post-explosion. And because we see such strong silicate features, we know it must be pretty optically thin. And so the star here is measuring the 2 sigma sort of lower limit on the radius. And this is well beyond the sort of typical shock velocities for a supernova. And so this is sort of why we are leading towards the interpretation that this might be an infrared echo. And that, in fact, the dust is just being heated and where the pre-explosion dust is also tracing this pre-existing dust. And so, as Melissa was talking about earlier, this is a plot of the dust formation, the dust mass over time. And so this is mostly JWST data, so including O5IP, which also shows silicate, and along with some other 1BN supernovae. And so 2023 XGO is a 1CN supernova, which Kyle Davis has triggered a DDT on and has a poster. So I'm going to advertise a little bit there. And what's really remarkable is that 2023 FYQ and these other 1BN supernovae sit sort of in the same space and seem to produce a very similar amount of dust, even though we know that O6JC likely sort of formed newly formed dust as well. So that's kind of a bit of a coincidence there. And so just in summary, 2023 FYQ is a dusty 1BN supernova progenitor. It's the first JWST observed supernova progenitor. There is significant pre-explosion dust, but the supernova is very blue and so little reddening, which kind of also agrees with it being an infrared echo. Yeah, and the dust is distant. So we think that this mass ejection must have been hundreds of years before the explosion. And so we think it's unrelated to this 4-year outburst. And so this was a very unstable progenitor star before it exploded. And the post-explosion data reveal likely silicate and carbon dust. And we interpret that as an echo. And that's my talk. Thank you for listening, and I'll take any questions.
Well, that's okay.
Very interesting object. How normal is it as a 1BN in the optical around P? Similar to other 1BNs, or is it?
It reaches a similar luminosity. It declines a bit slower than 06JC, which maybe that's not a typical 1BN. But we don't see a strong sort of, we don't see a strong near infrared excess, but the light curve is fairly similar. The spectra show probably a lot of electron scattering, so they have really broad features. Yeah.
Thank you very much for the interesting talk. I don't know much about molecular gas modeling, so I'm wondering if you can talk a little bit more about this. So do you do a complete chemical equilibrium in your plasma state, or do you do individual transitions?
So I'm fitting models similar to Melissa's paper. So I'm using the equations there and fitting just silica and carbon dust. I'm not doing any radiative transfer. Yeah.
Do you see any emission lines from the powering source, like nickel or?
Yes. So we looked in detail at the spectrum. It's very difficult because it's very deeply embedded in the host galaxy. So the host galaxy subtraction has been very difficult. But it's likely that, I mean, we looked at sort of a lot of features and we don't see anything but beyond a few narrow host lines. We're just seeing sort of the just features, we think. Yeah, but that would be super cool.
I suppose if the dust was too close, it would be destroyed by the supernova radiation itself. So can you say how far distant it is and when it could have been produced by the progenitor? Do you have experience on that?
Yeah, so I've given like a conservative limit, a 2 sigma limit, but looking at the data, like I think we need to sort of push that back because I think it's at least, if you assume the material was ejected at like 1,000 kilometers a second, then you'd put it at sort of, it was, the mass was lost sort of several hundred years before the progenitor star. But yeah, we also have a JWST follow-up program to kind of continue to get MRS data. So we should be able to see the evolution of the system as well.
Thank all the speakers. Coffee and poster break until. I'll say that. Okay.
Before, actually, don't get up yet. I have a couple announcements. So, all right. So we're going to start the coffee break in just a few minutes. But before, this is my last announcement of the day, so I got to get a bunch of information. First of all, I sort of outlined this in the morning, but I'm just going to say it again. After the coffee break, I have posted in Slack a list of assignments to different breakout sessions. We're going to have 3 breakout sessions. One is for early time observations and TOO responses. That's going to be here. The other is for stellar mergers and transients and galactic transients. And that is going to be across the street in Bloomberg. And Armin Rest is going to lead you over there. If you don't know Armin, that's him waving. And Suvi's going to be leading as the scribe in this session here. Armin's going to be the scribe and your line leader over across the street. And I will be leading the dust and supernova remnant section back in Cafe Con, in the back part of the cafe. This is a little bit of an experiment. I've been to a couple meetings before where we've workshopped out white papers. Some have been more successful than others. I've never run one myself. I didn't even want to run one here. But we, as an SOC, did want to run one. And, and I am a very democratic person, and I enjoy when everybody participates. And so that's what we're going to do. We're going to try to get everybody involved. And I really want you to take this seriously. It's going to be a chance for us to lock ourselves into a room, have some fun conversations, make a wish list, but it's more than that. This is a serious note. I look around and I see other parts of the astronomical community coming together, and they're very well organized, and they're able to advocate for themselves and really get a lot of money and telescopes and resources. And I think the time domain community is doing that. And as you saw earlier, we're going to say this a few times, there are a series of TDAMM workshops that is working towards this exact goal. And I was involved in one early on, and I haven't been involved in the last two. I want to get more involved in that. This is sort of an offshoot, independent, but hopefully we can compare and combine notes. But I think that the time domain community really has to start advocating for ourselves and to get onto the same page. This is going to become more and more important in the next few years as Rubin and Roman come online. I also have not been a huge part of the Rubin conversations. I'm trying to get more involved now myself. I am, if you're not aware, my functional hat here is as the deputy project scientist for the Roman telescope out of the Space Telescope Science Institute. Project scientist is a complicated name, but I am the deputy project scientist here. And that part of that role is to really engage and to encourage community participation. How we are going to share that data, work together on these large data sets, coordinate follow-up opportunities, use different types of telescopes, enter into a new era of big data, machine learning, AI. These are all, I think, very intimidating and big and open questions, but we're not going to be able to tackle them unless we're really all sitting in a room and thinking through some of these answers. I don't anticipate we're going to have all the answers today, but I do hope that you take it seriously enough that you don't, just sort of throw out a lot of maybe the first things that come to mind. I really want you to dig deep. That's what I'm saying. And so the scribes are going to help you. The chairs have these instructions as well, but I just want to read out some of the questions that I really want us to try to put down into paper. How would, insert this topic, inform strategy for current space telescope, STScI space telescopes, or those in prep? What synergies with other space and ground-based or multi-messenger facilities existing in prep, hypothetical, are needed to forward this topic? What theoretical, computational, laboratory, or other forefront methods need development to forward this topic? And with these needs, what risks exist if not addressed in the 2020s or early 2030s? Like I said, I haven't been thinking about a lot of these, so that's why I'm here today. And we have incredible leadership from across the community. We have senior level project membership from a number of space-based observatories. We have representation here at Space Telescope, also ground-based observatories, a lot of junior and mid-career people thinking ahead. So I really think we have a lot of the right ingredients to get out what we want. So, that's sort of my last petition as you go into these breakout sessions during the afternoon. Like I said, you're going to have a chair, you're going to have some spark talks to get the juices going, and then you'll have an hour of conversation to get as much down on paper as you can. Question in the back, yes. Yes, and so the rooms one more time, if you haven't signed up, if you have signed up, your name's on the list. If you haven't signed up, the Stellar Transients, Mergers, and Galactic Transients is across the street in Bloomberg. Armin Rest is leading that. That is meet in the lobby about 10 minutes before you have to go over. So at 3:35, okay? That is filled. So if your name's not on that list, that room is at capacity. This room is going to be the breakout for early time observations and TOOs. That's going to be scribed by Suvi Ghazari. She can raise her hand there. You also have your chair. But you can just come back here. This is as many people as we need can fit into here. And in Cafe Con, I'm going to be leading a group on the supernova remnants and dust and mid-IR observations and things like that. And so those will all commence at 3:45. Like Armin was saying, to go across the street, you need about 5 or 10 minutes. So meet about 10 minutes early in the front lobby where you came in this morning. Okay, And then just a couple, so that's all I have to say about the breakout sessions. Any questions on that? Okay. Tonight, like I said, after the welcome reception, me and whoever else, we at about 7:30, whenever the thing winds down, we can head over if you want to Union Craft Brewery. It's about a 7-minute Uber ride. Plenty of tables. If you're still hungry, they also have food. And a final reminder, tomorrow we are doing the tutorial with Michael Coughlin and Will Bonneau. I don't know if either of you want to I already gave your blurb, but I don't know if you want to make a quick statement. People have asked, you don't need to download anything or do anything to prepare. You just need to come with your laptop. And this will be sort of a foray into machine learning and AI algorithms. And you can actually start using some software and packages. And then at 9 o'clock, to transition into that, we are going to have a representative from our Roman mission office here, Gisela De Rosa, who will give you some exciting updates about our cloud platform technology that we are developing for Roman. It is called the Roman Nexus. It's where we hope people will be working with their large data sets, and that's due for launch this summer. So she's going to give you a sneak preview and some demos and walk you through all of that. And then we're going to roll right into high redshift transients, and I think that kickoff talk is going to be Justin Pirel at 9:15 a.m. So we're just getting going. The excitement continues, and thank you all for all your hard work today. And let's go enjoy some coffee. Yeah.